This video is recorded to help my students to understand how to solve linear homogeneous recurrence relation. So first, let's see the definition. What is a linear homogeneous recurrence relation? We said that a linear homogeneous recurrence relation of degree k has the following form: Fn equals C1 multiplied Fn minus 1 plus C2 multiplied Fn minus 2 plus go to the ck multiply Fn minus k. So basically, equivalency one term is a linear combination of its previous k terms. Okay, so here Cj, j equal 1 to k, they are constants and not depend on n. And ck is not 0 because you want the degree is k, so which means the Fn has to be related to the k terms before it, in front of it. So let's say example. For example, if you have Fn equal 2 times Fn minus 1, then this is the first order linear homogeneous recurrence relation with C1 equal 2. Okay, so in this sum, you only have one term. That means Fn only related to the term in front of it. So let's say second example, Fn equals 3 Fn minus 1 plus 10 Fn minus 2. This means each term is a linear combination of its previous two terms. Okay, so this is a second order linear homogeneous recurrence relation with C1 equals 3 and C2 equal 10. Now notice when we say linear, which means no terms multiplication there, no square or some power other than 1. This is one power, right? Other than 1, those power for the terms. For example, this is not a linear. Fn equal Fn minus 1 multiply Fn minus 2. So this is not a linear, okay? Because you have two terms multiply to get the next term. So this is not a linear. Now, what means non-homogeneous? Let's say this. Fn equals 3 Fn minus 1 plus 10 Fn minus 2 and plus n. This is linear, but it's non-homogeneous because you have you plus a n, which is not a term in this sequence. So this is not homogeneous. So for this course purpose, I just need a student to understand how to solve linear homogeneous recurrence relation with first order or second order. So in order to solve this linear homogeneous recurrence relation, we first need to understand a key concept is called characteristic equation. So a characteristic equation of the linear homogeneous recurrence relation, if this relation is this form, then his characteristic equation is this, is r to the n power minus c1 r to the n minus 1 power minus c2 to the r to the n minus 2 power minus until minus ck equals 0. So this is a polynomial equation. If you look at this, it's very easy to remember, right? Equivalency, the coefficient of this n degree polynomial equation is just the coefficient of all those terms. The term of Fn, his coefficient is 1. The term of Fn minus 1, his coefficient is negative C1 if we move this everything in this equation to the left side, okay? To the left side. Then you can say this for the power n minus 2 is just a coefficient of Fn minus 2. So this is easy to get characteristic equation if you give me a linear homogeneous recurrence relation. Now let's say example. So if your recurrence relation is Fn equal to Fn minus 1, then its characteristic equation is r minus 2 equals 0 because this is the first order. So your equation is only have first order, which means linear equation, right? Now for this one, Fn equals 3 Fn minus 1 plus 10 Fn minus 2 has characteristic equation is r squared minus 3r minus 10 equals 0. Okay, so we first understand this key concept, characteristic equation. Then we need to understand the general solution, how to find the general solution. So, like I said, we only consider the first or second degree linear homogeneous recurrence relation. In order to solve the first degree linear homogeneous recurrence relation, to get a general solution, we only solve the corresponding characteristic equation and assume since standard equation is a linear equation, it must have solution, right? Suppose the solution is R, then the general solution for this recurrence relation is Fn equals C to the R, C multiply R to the n power, where C is a constant, which means you have infinity solutions. Any constant C will give different constant C give you different solution, right? So we call this form is a general solution. To solve second degree linear homogeneous recurrence relation, again, we first solve the corresponding characteristic equation. Now, since this time characteristic equation is a quadratic equation, so there are two cases. Either there are two distinct solutions, R1 and R2. Notice they're distinct, but they don't have to be real. They don't have to be real. You need to understand this, okay? They don't have to be real. They could be complex, but normally in our case we only give you real solution. So if you have two distinct real solutions, R1, R2, then the general solution will be Fn equals C1 multiply R1 to the n power plus C2 multiply R2 to the n power, where C1, C2 are constants. So again, if you have different C1 and C2, you get a different specific solution. So that means this general solution shows you have infinity solutions. But in real life, we will solve the recurrence relation with some initial condition, which means with those initial conditions, we will be able to specify those C1 and C2 be a fixed constant. Okay. The second case, we have two repeated solutions R. So then in this case, the general solution is Fn equals C1 times R to the n power plus C2 multiply n multiply R to the n power, since you only have one solution R, right? So again, but we still is a linear combination of two terms. One term is R to the n power, another is n multiply R to the n power, okay? So let's see example. To find a general solution of the following recurrence relation, the first one is Fn equal to Fn minus 1, another is Fn equals 3, Fn minus 1 plus 10 Fn minus 2. The third example is Fn equal to Fn minus 1 minus Fn minus 2. Okay, now this is a first order linear homogeneous recurrence relation. The rest two are second order linear homogeneous recurrence relation. Let's see the solution. To solve the first one, we first find its corresponding characteristic equation, which is R minus 2 equals 0. The solution is R equal 2. Then the general solution will be F sub n equal C multiplied 2 to the n power. Now, it's easy for you to check this really is a solution. How do you check? You just plug this solution into the equation, see if this equation is true or not, right? For example, you substitute this solution to this equation. So on the left side, which is Fn, which is C multiplied 2 to the n power. On the right side is 2 times Fn minus 1. What is Fn minus 1? Based on this general solution, Fn minus 1 will be C multiplied 2 to the n minus 1 power. 2 to the n minus 1 power multiplied 2 will become 2 to the n power. So the right side is also C multiplied 2 to the n power. That's why these two sides are equal. So this is a solution, okay? Now for next one, we first find his corresponding characteristic equation, which is R squared minus 3R minus 10 equals 0. So we want to solve this quadratic equation. We factor it, which will be R minus 5 times R plus 2 will equal 0. We solve it R equal 5 or R equal negative 2. Then the general solution will be Fn equals C1 multiply 5 to the n power plus C2 times negative 2 to the n power. Basically, those two solutions of the characteristic equation, they are the base of those power. Okay, again, student can check this really is a solution for this recurrence relation. Okay, you can check it. Now, when you check it, you just need to do very simple algebra calculation, right? You will find both sides are equal. Okay. Let's see, the next one is Fn equal to Fn minus 1 minus Fn minus 2. The characteristic equation is r squared minus 2r plus 1. Notice that this is plus 1 because when you move this term to the left side, it will change to plus. So it's plus 1 equals 0. The solution of this equation is r1 equal r2 equal 1. So it has a repeated solution. Then in this case, the general solution is Fn equals C1 times 1 to the n power plus C2 multiply n times 1 to the n power. Since 1 to the n power is always 1, so the solution actually is C1 plus C2 multiply n. So this is a general solution. So you already say, if the first order recurrence relation, his general solution contain one constant. The second order, the general solution will always contain two constants. Now, we need to specify these constants. We need an initial condition. So let's see how to solve with this equation with initial condition. To find a specific solution for n degree linear homogeneous recurrence relation, we need to have n initial conditions. Now, since we only ask a student to understand how to do it for first degree and second degree, right? Then we only need one initial condition for first degree and two initial conditions for the second degree. For instance, find a closed formula of Fibonacci numbers 0, 1, 1, 2, 3, 5, 8. You can say Fibonacci numbers, you start from 0 and 1, then each term will equal the sum of previous two terms. So this is a recurrence relation. Equation say the nth term equal its previous sum of its previous two terms, which is Fn minus 1 plus Fn minus 2. This is a linear homogeneous recurrence relation to represent the Fibonacci number, but also need an initial condition, which means f0 equals 0 and f1 equal 1. Okay, so really depends on how you want to call it. We like to say this is when n equals 0, so we say f0 equals 0, f1 equals 1. You can test if you want to call it with different. You want to call it this is f1. Then your formula need to change accordingly because when n equals 1, you will get a value 0. Okay, here we still call f0. That means when n equals 0, we get a 0. When n equals 1, we get a 1. When n equals 2, we get a 1. When n equals 3, we get a 2. So that's, we say the initial condition is this. Now, in order to solve this one, we first solve corresponding characteristic equation, which is r squared minus r minus 1 equals 0. Now, this one have two solutions by using quadratic formula, which is the solution is negative b plus minus square root of b squared minus 4ac over 2a, where a, b, c are the coefficient of this quadratic equation. So the coefficient a is 1, b is negative 1, c is negative 1, right? So we use quadratic formula. The solution will equal negative b, which is negative 1, which is 1, plus minus square root of b squared, which is 1, minus 4ac, 4ac, which is negative 4. 1 minus negative 4 is 5. So square root of 5. So you have those two solutions. Then the general solution of Fn is C1 constant multiply the first solution raised up to n power plus C2 multiply the second solution raised up to the n power. Okay. Then we use the initial condition to find C1 and C2. So when we apply the initial condition for f0 equals 0, f1 equals 1, so we first let n equals 0. We suppose get a 0. So when n equals 0, any number, its 0 power is 1. So equation you have C1 plus C2 equals 0. Okay? Then when n equal 1 will equal 1. So when n equal 1, 1 plus square root of 5 over 2, its 1 power is still 1 plus square root of 5 over 2 multiplied C1. Then again, this 1 power is 1 minus square root of 5 over 2 multiplied C2 equal 1. So you need to solve this linear system. Okay, you have two unknown, C1, C2, you have two equations, so you can solve it. From the first equation, you know C1 equal negative C2, then I plug this into the second equation. Remember C1 equal negative C2, okay? So then you replace C1 by negative C2, then you combine those, then you will get negative square root of 5 of C2 equal 1. That means C2 equal negative 1 over square root of 5. So C1 equal 1 over square root of 5. Then you plug C1, C2 back to the general solution. Then you get the specific solution for this recurrence relation with this initial condition, which this is the closed formula for Fibonacci number. Equation say, you give me an n, by this formula, I can calculate, I can tell you what is the nth Fibonacci number. Notice n start from 0. Okay, if you feel interested, please go ahead and check several answers for the Fibonacci, the first several terms of Fibonacci sequence. Okay, if you have any questions, please give me an email.